Welcome back, physics fans, and we are going to do another power question here. This is going to be for Physics 11, question number 6 from the power worksheet. How much power does a 45-kilogram person develop climbing up a vertical ladder that's 7 meters high? And then there's two conditions here. First one, let's take a look at it. If the person climbs at a constant speed and it takes them 7 seconds, use the force applied equals the force of gravity. Okay, I'm just going to draw a free body diagram just to understand what we're doing here. Not that you have to here, but there is the force applied, and that's the force that the person's generating, and that has to equal the force of gravity because the acceleration is zero. Okay, why is acceleration zero? Because it says it's a constant speed. Okay, so the force that the person is pushing up with is his force of gravity, which, or her, or whatever, 45-kilogram person is, and that's 45 times the gravitational field strength of 9.8. Mr. Calculator, can you help me, please? 45 times 9.8 is 441. So this is 441 newtons. And by the way, that is an upward applied force that he is or she is climbing with. Okay, so now we're trying to find out how much power. Power is equal to work divided by time. Okay, the work in joules, time in seconds. If you put them in those two units of joules and seconds, then you get the power of watts out. Okay, so we'll just do that in joules and seconds to get watts out. So the work is going to be the force times the distance moved. Okay, the work is going to be that. Now this force is upward, that's what he's applying, and the distance is upward, so we will get a positive amount of work. There's no angle between them. And so the force is 441 newtons, and the distance up is 7 meters. So the work done is 3,087. What's the unit here? It will be joules. And what's the direction here? There is no direction. It's a scalar. Okay, it just has a positive because the direction of the force and the direction of the displacement and the distance is the same. So the power is going to be the work over the time. So the work is 3,087 joules, and the time it was told was 9 seconds. Okay, so we take this number and divide it by 9, and we get 343. And what unit is that? Watts. What's the direction of that? It's a scalar, has no direction. Okay, so that's the end of A. Let's take a look at B now. B, there's an acceleration now. So doing the whole thing from scratch again, but acceleration assuming starting from rest. So there's an F applied, there's a force of gravity, and that force of gravity is, there's my free body diagram. I don't want to mess it up by drawing other things inside it. The force of gravity is 441 newtons. We figured that out. But now the F applied is going to be greater than that because there's an acceleration up. So Newton's second law says, let's change the red here because we're on a different question. The sum of the forces is equal to F net, which equals ma. So the F applied minus the force of gravity, the losing force, is equal to m times a. Okay? So the applied force has to equal the force of gravity, which is 441 newtons, plus the mass, which is 45 kilograms. That's the mass. And the acceleration is 0.25. That seems like a very slow acceleration. Nice. Okay. And if we do this, 45 times 0.25 will be 11.25. So this is 11.25 newtons up, and that's going to be the net force. Net force. We have to add the 441 to it, and we get 452.25. Let's just drag this over here. So the F applied is going to be 452.25. Okay, and that'll be in newtons, and the direction of that is up. So the work, let's change to red here again. The work is equal to the force times the distance. Okay, so what do we do there? Well, just take that force times the distance of 7 meters. It doesn't change if you're accelerating up it. So the work is 3165.75 joules. Just slightly a little bit more. We had 3087, and now we have just a little bit more to accelerate. Okay, but here's a little bit of tripping hazard. It's not going to take them 7 seconds to get up, or 9 seconds. It's going to change. So we have to go back and do kinematics. The acceleration is 0.25 meters per second squared. The distance up the ladder is 7 meters. We have the initial speed is equal to 0 meters per second, and we need the time. Okay, so we will use a formula of d equals bit plus 1/2 at squared for this kinematics. And the initial speed is 0, so this term disappears. And to solve for time, time is going to equal the square root of 2d over a. So that's going to be the square root of 2 times a 7-meter ladder all over the acceleration of 0.25. Mr. Calculator, I don't like doing square roots in my head. Square root of 2 times 7 divided by 0.25. And this is 7.483 seconds. So that will be the time, the new time for this part B. So there's 2 new things in this part B. Is how much applied force there will be, and therefore, and also the time. So let's get back and let's finish up the power question. Power is equal to the work over the time. The work done is 3165.75 joules, and the time is 7.483 seconds. So we take those two numbers, that number divided by that number, and we get 423 watts. So let's just view this out at 125 so we can see a little bit more of it. So this power is, what did I say? 423. Okay, so the output is significantly more. Let's take a look at highlighted blue. It was in A, 343, and in B, I shouldn't highlight that in blue, highlight it in yellow, and in B, it's 423. Thank you very much for watching. Subscribe, smash that like button, turn on that bell notification because you never know when the algorithm of YouTube shunts you away from watching good physics to being bad physics. Thanks for watching.